Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Well, thank you for having me here. So today I'm going to talk about some algorithmic issues in scheduling for a multi-carrier wireless environment. And the work was joined with Matthew Andrews, who's also from Bell Labs. Right, so before getting into multi-carrier scheduling, so let me first talk about what is a single carrier scheduling. So in a single carrier environment, what we have is one carrier and end users and a time-slotted system. So the job of the scheduler is to decide for each of the time slot which user the scheduler would service. So here's a schematic picture to describe the single carrier system. So at each time step, the arrival is described by this arrival vector. AIT is the amount of data arriving for user I at time t. There's a queue vector. QIT describes the amount of data waiting for the queue for user I, and there's a service rate vector, which says if user I should be chosen by the scheduler, then the amount of data equivalent to Ri of t will be draining from user I's queue. So because this is a wireless system, the service rate vector is both user dependent and time varying, just because the users will be mobile for the most cases, and the channel conditions would also change. So this single carrier scheduling environment is meant to model systems such as the CDMA EVDO technology. In the EVDO, the time is slotted in a way that each second into partition about 600 slots, and for each slot, the scheduling decision will be made. So here's a base station. Here are here's one mobile, one of the many. So each mobile would measure the downlink signal to noise strength and calculate the rate at which it can receive signal from the from the base station, and send this information to the base station. And from all the information collected from different users, the scheduler here is going to able to make a decision. In particular, for EVDO, there are these discrete rates at which the base station can send data to the mobiles. Now, moving on to a multi-carrier scheduling system. So instead of just having one single carrier, now we have multiple C carriers. Still, we have end users and a time-slotted system. So what happens here is that the scheduler has to decide for each carrier at each time slot which user it's going to serve. The constraint, just because how the wireless system is set up, that each carrier can only serve one user per time slot, but it's possible that multiple carriers would choose the same user to serve during a slot. Yeah? So again, to look at the schematic picture, the arrival vector and the queue vectors are the same, except that for the service, instead of having a service rate vector, we're going to have a service rate matrix. So the matrix RIC of t is the amount of data that user I would receive from carrier C at time t if the scheduler decides that this service relationship is going to happen. And typically, one can imagine this number is both user-dependent, carrier-dependent, and time-varying. The motivation for having a multi-carrier scheduling system is to model the OFDM-based wireless systems. That's orthogonal frequency division multiplex. So examples of such systems will be Wimax, or UMB, which is the next generation EVDO, or LTE, which is the next generation UMTS. Okay, so for both single carrier and multi-carrier scheduling system, there are two different philosophies. One can do slot-by-slot scheduling, or one can do a template-based scheduling. In the slot-by-slot scheduling, a decision is made every single time slot. So the advantage is that it adapts quickly to the changing traffic or changing channel condition, therefore the changing service rate, either vector or matrices. But the disadvantage is that there's a fairly large overhead, both in terms of communication as well as computation in order to make a decision. So the counterpart is called the template-based scheduling. Well, the template-based scheduling is that we make up a schedule for a frame of T slots. So T can be a number like, say 50. And then this template scheduling can be repeated over time. So you kind of compute a schedule for multiple time slots, and you repeat this slot over time. So obviously there's less overhead, both in terms of communication as well as the scheduling, the algorithmic computation. And what's it good for is if you view the traffic pattern as fairly steady, and for the channel condition is also fairly steady. So if it doesn't change much, then overall you're better off with the template schedule.
So when you say smaller overhead, are you implying that if I'm only making one decision for every T slots, then the users, I only need to get the channel condition every T slots?
Could even be less. Suppose I compute a frame of T slots and I use it 5 times. So only at the end of 5T I will recompute.
So
Yeah, yeah. So, okay. So there has been lots of work in the single carrier scheduling. Multi-carrier study is relatively new. So what we want to do here is see how we can transfer our knowledge and the results known in the single carrier schedule into the multi-carrier situation. So first we'll look at the slot by slot scheduling, and some of the work was presented in MobiCom last year. And a large part of this work is to focus on the multi-carrier scheduling. One difficulty is how to prevent the over-allocation of resources, and that's what the objective of the work is. So let me explain. So let's first look at a very popular algorithm for the single carrier scheduling. Remember, this is the schematic picture. And one straightforward and very popular and good algorithm is called max wait. So max wait is the simple algorithm that works as follows. At each time step T, the scheduling algorithm would choose the user I that maximizes this product. This product is the queue and the service rate product. So the motivation is if a user has a fairly long queue, then possibly it's good to serve it. And if the user has a very good service rate, then it's opportunistic. It's a good opportunity to serve it as well. So alternatively, we can modify this objective function a little bit, because if, say, the rate is fairly large, and in fact is larger than the queue, then the benefit you get is actually the minimum of the queue and the rate. Yeah. So alternatively, you can just choose the user that maximize this product. And in this way, you can avoid resource wastage. Now, even though this algorithm is extremely simple, it has a very desirable property, which means called stability. This is saying if stability basically means the amount of data that's present in the system is bounded over time. It's by a quantity independent of the time. So if the total data follows this blue line, then this algorithm is stable. But if it kind of grows and bounded with time, there's an unstable algorithm. Then many groups of people, starting from the early 90s, have shown that max wait algorithm in fact is stable whenever possible. And overall, the idea is that the potential function, which is the sum of the queue square, has a negative drift if the queues get really big. So therefore, using this method of analysis, it's able to find an absolute bound for the queue size. Okay. So naturally, one would wonder, what's the way of generalizing this max wait algorithm from single carrier?
Quick question.
Yeah.
Is max wait throughput optimal?
Throughput optimal.
That is, it can stabilize any arrival vector.
Not any. Not any. So,
given that it can be stabilized.
Okay.
Some algorithm.
Yeah. So certainly, if say the arrival vector is say has a nice stochastic probability, it's say ergodic or something, yeah, then it can stabilize any such input vector. And that's also been studied on whether or not max weight is even stable if the arrival is adversarial. So I think there's also some progress on that front as well.
Okay, I guess my question was, has anybody shown that the max weight algorithm has perhaps the largest stability region?
That I'm not sure.
Okay.
That I'm sure. There are other algorithms like proportional fair under a different assumption that has like a good utility property, maximize the sum of the log, for example. Yeah. So for max weight, let's just say what's the first cut transformation from the single carrier to multi-carrier. So the simplest thing to do is to treat each carrier independently. For each carrier C independently chooses the user I that maximizes the sum of the product, which is the Q times the rate. And let's use I of T to be the sum of the rates that get assigned to user I across all the carriers that are assigned to I. Okay, now one can show that fairly straightforwardly that in fact this algorithm would maximize this quantity, maximize Qi of T and I of T. And in fact, the same stability proof would follow through as well. So one might think maybe that's the end of the story, except that maybe we want to see, in fact, would say every carrier be in fact choosing the same user if the user should have a very good R or something. So the total rates, in fact, would be more than the Q size, then it will be a wastage. So maybe the objective would be more sensible to maximize the sum of the Q and a minimum of the total rates and the Q size. So that would be a natural, more sensible objective to maximize. So, and as we've seen that in the single carrier situation, this objective can be achieved very simply. However, just by introducing this very simple twist, we can in fact show that this objective becomes NP hard to optimize. And worse yet, it's possible to find a small constant so that no approximation algorithm can get as close to optimal as this 1 minus epsilon. So let me just try to give you an indication why where this hardness comes from. So we can make a connection to this problem called generalized assignment problem, GAP. So this problem states as follows. You have a bunch of bins and you have a bunch of items, and you want to put items into bin. Each bin would have a size of bi, and each item would have a size that's dependent both on the item and the bin. That's where the generalized part comes from. So it has a size SIC, and once you manage to put the item into the bin without exceeding the total bin size, you get a profit, PIC. So we can relate this bin to the users in our problem and relate the items to the carriers. And also the bin size will be the Q length, and the profit would also, I think the profit would also be related to the Q length. So therefore, making this connection, we are able to see that just having this simple twist, all of a sudden our problem cannot be solved, optimized exactly. So then what do we do? So fortunately, this objective function to solve this problem falls into a special case called maximizing a submodular function over a matroid. And if the optimization problem fits into this framework, the good approximation algorithm have been known for decades. So let me explain what this green line is. So I need to explain what a submodular function is. I need to explain what a matroid is. Once I've explained that, I'll tell you what a good approximation algorithm is. So what is a matroid? Matroid is typically defined over a ground set. Let's call it an omega. And this I is a matroid if it satisfies the following two conditions. So if any element of I, so A is an element of I, so A would be a subset of the ground set. And so suppose A is an element of this I, and B is a subset of A, and B is also an element of I. So this sort of, there's enclosure downward. And if both A and B are elements of I, and A is bigger in size than B, then we can find an element that's in A but not in B, so that we can augment B with this element A, so that the augmented set is also an element of I. So in that case, I becomes, we can say I is a matroid. So a simple example we can view, so suppose we have a graph. And the ground set would just be the edges of the graph. And an example of a matroid would be a collection of the forests from these edges. That would be a matroid. You can see that if you have a forest which is A, and if B is a subset of A, B would have to be a forest as well. So therefore, it's in the matroid, and you can check the second condition holds as well. Okay, so what's a submodular function? Submodular function is defined on a set. So it says if for any sets A and B, if the function defined on A union B plus the function defined on A intersection B is at most the set is at most the function defined on A plus the function defined on B. If this relationship holds for all the subsets A and B, then the function is submodular. Okay, so enough of definition. So I guess it's not so important that you know exactly what these are. You only need to know there's a matroid and there's a submodular function. Now, so suppose you happen to be in this nice framework of trying to maximize a submodular function of a matroid. Now, in the 70s, these people, Fisher, Niemenhauser, and Woolsey, showed that there's this very simple greedy algorithm that would do a lot of the work. So as it indicates, it's how you build a greedy solution is as follows. You begin with an empty solution, and every time you repeat the following process until you cannot do it anymore. At every step, you try to choose an element that's not already in your solution, and you try to augment it. So suppose from your current solution, you augment it with one more element. Now, so therefore, you will see a progress in your objective function. So measured by the difference between the augmented solution and the original solution. If the difference, so you can try it over all the possible elements, and you're going to choose to augment your current solution with an element that maximizes your current step. So every step you try to make your solution so that it makes the best local progress. So that's your greedy algorithm. So a very simple, typical greedy algorithm. However, even though it's simple, these people have shown that this algorithm would give you a half approximation to the absolute optimal, as long as it fits, as long as this problem fits the framework of maximizing a submodular function f over a matroid, which if all these things form a matroid. Okay? So now let's see how this wonderful result applies to our framework. Okay, so what we are trying to do is we're trying to decide how we are going to assign carrier and time slot pair to all the users. So let's try the following greedy algorithm. So for each time step t, we're going to process carrier one by one. So what we are going to do is we're going to serve a user I that maximizes the product of the Q and the benefit. Now, the benefit now is how much of a Q I can reduce. And so the maximum amount I can reduce is the rate. But it's possible that the previous carriers could have eaten up lots of the Qs already. So at this moment, we use RIT as the running sum of how much rates the carriers so far have assigned to user I. So this is the service that user I has received so far, and Q minus that is the maximum amount that the current carrier could serve this user. So you take the mean of these two quantities, and the carrier C would serve the max of these two products. Okay, so apparently this is a greedy algorithm, because every time it does the local best. So all we need to see is whether or not this whether or not the framework fits into the matroid, maximizing submodular function of a matroid. If it is, then we know that this greedy algorithm, even though it may not get you the absolute optimal, it gets you halfway at least. Okay, so there are three things I need to verify. First, I want to verify that the setup is in fact a matroid, and I define the matroid as following. The element in my ground set is a collection of the user and carrier pairs. Okay, so this is my ground set, and what my matroid is a subset of all the elements in the ground set, as long as each carrier appears at most once in A. So now what does that mean? If each carrier appears at most once in this subset, that means in fact it's a valid solution, right? For any scheduling policy for multi-carrier, all I care about is that each carrier can serve at most one user per time step, but each user may receive service from multiple carriers. So in fact, this is saying all the valid schedules over this ground set actually form a matroid. So I look at all the possible valid schedules. And this function f simply tries to choose one element in the matroid, which is A, such that this objective function is maximized. So one can verify this is a matroid, and this objective function is in fact submodular as long as I restrict my solution to be a valid schedule. And algorithm 1, as we can see quite apparently, it is a greedy algorithm. So therefore, we can apply this nice hammer from these three people, and we know that in fact this algorithm 1 is always within a half factor of the absolute optimal solution. And then there are other ways to get half approximation. Here's another example. So instead of processing carriers one by one in a greedy manner, one can process users one by one in a greedy manner. At every time step, we can find a subset of carrier to assign user I so that this objective function is maximized. However, the trick is every time we move to the next user, if we locally try to find the subset of carriers that's the best for the user, it's possible that a later user is trying to use a carrier that's been used already in the past. If that should happen, then we need to make a decision as to which user gains more by keeping that carrier. So at each time step, one needs to make a decision there also. So the analysis takes the same route, although one needs to define a different matroid. And this matroid, the ground set, associates each user with the set of carriers that can serve the user. And the matroid is defined on the ground set if each user appears at most once. And then again, we can show this is a submodular function, it's a greedy algorithm, and therefore we get a half approximation. So there are lots of details there, but we are not getting into. So to finish the first half of the talk, I just want to show you some simulation result. So the simulation result is trying to see, so the trace comes from, I think it's a simulated data trace for multi-carrier, for a multi-carrier system. So we have two objective functions. One is an easy objective function. We know exactly how to solve optimally with a simple algorithm, but it may produce resource wastage. And we have a more sensible objective function, which tries to take the minimum of the total rates received in a queue length. However, we know this objective function is NP hard to get. Nevertheless, we have a half approximation. So are we better off to use an exact algorithm for a not so good objective function, or are we better off to use an approximate algorithm for a better objective function? So, so these two plots, the x-axis is the time units, the y-axis is the total queue length. So as we can see that if we use the exact algorithm for a not so good objective function, the total Q is much larger than if we use an approximate algorithm on a more sensible objective function. So the Q is much smaller in that case. Okay. So now I want to move on to the second part of the talk. So let me just wrap up the first part of the talk. First part of the talk, we're trying to do a slot-by-slot scheduling in a multi-carrier system. We almost directly generalize a max weight algorithm, which is known to be very good for a single carrier system to a multi-carrier system. There's a small twist in which with the objective of trying to avoid resource wastage. The simple twist makes an easy problem into an NP hard problem, but fortunately it fits into the framework, this nice framework of maximizing some modular function or matrix. So we use a greedy algorithm, which is known to work well for all problems in this category. So now moving on to the multi-carrier template scheduling algorithm. So let me remind you what the template scheduling is. So instead of making a scheduling decision every time slot, what we are going to create is a template. The template would consist of multiple time slots, say a big T, and this template can be repeated over time. So here, the color coding in each of the slot is the user. So there are 3 users here. So the light green, the green one, and the blue one. So it's this is saying the top carrier, the first time slot serves the light user, etc. So I also mentioned before as to when the template scheduling is desirable. It's desirable when we think the traffic is quite steady and the channel conditions do not change. So therefore, we can kind of use the same scheduling again and again to reduce both the communication overhead as well as the computation overhead. So because we assume the traffic is steady and the channel condition, therefore the service rates are relatively steady, we're going to drop the dependency on T for both the arrival vector and the service rate matrix. Okay. Okay, so for the template scheduling problem, in fact, there are 2. One could view this problem as 2 parts. One is to decide how many slots each carrier C are allocated to user I during this whole framework. So I use FIC to decide the number of carrier C token to assign user I. So in the previous picture, so the top carrier would have 2 slots assigned to light green one, 2 slots to the dark green one, and 0 to the blue one. And the second carrier would have 2 to dark green one, 1 to light green one, and 1 to blue one, etc. One is to decide how many. And so one way to decide how many is just trying to formulate it as a, say, optimizing precision problem using math programming. So if, let's say, A is the steady arrival rate for user I, then I can try to maximize the product of AI and a minimum of AI and this quantity. Now, this quantity is somewhat interesting. So as I said, FIC is the number of slots, and RIC is the rate. So if I sum over all the C's, so in fact, this is the amount of service user I would receive during a frame. So therefore, using the same philosophy as we dealt with in the slot-by-slot scheduling, there's never any point to assign user I more service than the arrival rate. So it only makes sense to do the min of these 2. And of course, the total slots added up is at most T. So if we formulate this how many problem in this presentation, in fact, it's very, very similar to the slot-by-slot scheduling. So we can revert to what we did for slot-by-slot to decide the issue of how many. So what I'm...
Excuse me, 1 second. So in this maximization, so this is done for each user?
Right. I guess.
Is there some?
Yeah, I think that's a summation there. Yeah, sorry. Sum of I, AI. Yeah, sorry. Yeah. Otherwise, it wouldn't make sense. Yes. Okay. So once we've done how many, then we need to know which ones. So for example, we know it's 2 light green is 2, but then still there are many different ways of putting it. So overall, one would say this looks like a better template than that. Well, one reason being, see, for this template, the service to the light green users are quite spread out. To the green user, dark green users are fairly spread out as well, and so is to the blue user. Whereas for this less good template, the light green user gets all its service at the beginning, so it's more bunched up. So is with the dark green user. So in a way, we want to spread out the allocations to user I so the delays are kept low. So here, in this case, you can see each user would have to essentially wait for a long time before its next turn. Once its burst is over, it has to wait for a long time. Okay, so there's a way of formulate this notion of spreading things out. In fact, this delay formula comes from network calculus. So let me try to explain what this formula is for. So there are notations we introduced in the past. FIC is the number of carrier C tokens assigned to user I within a template. T is template size. RIC is the service rate that user I would receive from carrier C. Now this new quantity, Ni of T, is the amount of service received by user I by time T. So we just try to calculate the cumulated sum. Yeah? So now let's see.
So the amount of service is in terms of the total amount of rate user I has?
Yeah, so it's, the units are not consistent. So the rate, one can imagine, yeah, so rate, one would say it's sort of bits per second, but let's just say it's bits. Yeah, yeah. Okay. So so let's just look at this formula, and then I'll give you an example and see if it makes sense. So if we look at an interval between S and T, okay, so NIT minus NIS is the amount of service that the user receives between S and T. Yeah? Now we want to normalize it. So what's in the denominator? So the summation is over all the carriers, RIC times FIC. So as we have seen, this quantity is the total amount of service the user I would get over all carriers, right? Because the first carrier gives I1 times Fi of 1, the second carrier. So this sum is the total amount of service the user I would get during a frame. But the frame consists of T steps. So the average rate the user I would get over a frame is this thing divided by T. And this is the service it actually gets. And this is divided by the idealized rate. So if I look at the difference between the time interval, which is T minus S, and this would tell me how much I fall behind. So let's look at a special case. Suppose T and S happens to be in the entire frame. So the difference between T and S is big T. Yeah? So during big T, Ni of big T minus Ni of 0, in fact, is the whole service I received, right? During a frame, I know the total is this. And if I divide it by that, what's in the denominator, this term actually gives me big T. So because when T and S is the beginning and end of a frame, this and that sum actually is the same. So therefore, this term gives me a big T, and the first term is a big T. So this is saying that the service always catches up if you look at an entire frame, by definition, except that what I'm interested in is how much I fall behind within a frame. Of course, I can be ahead in terms of the service I receive, but there are bound to be time that I'm behind. So I'm trying to get service as spread out as possible, so I fall behind the least amount in comparison to the idealized steady stream. Okay, so this is the definition of the delay of user I, and similarly we can define the delay of user I with respect to the service that get from carrier C. It's a very similar definition. And we can show that EI is in fact at most EIC maximizing over all the carrier C. So this gives us an idea that maybe the way to do it is maybe we should minimize the end-to-end delay with respect to each carrier C. And therefore, with this relationship, we have certain bound on the user I across all carriers. Yeah? So this sends us back to what can we do for a single carrier situation? How do we create a single carrier template so that the tokens are spread out as possible? So I've rewritten this problem with respect to the single carrier situation, so it's easier to think about. Now I dropped the connection to carrier C. So Fi tokens for user I in template of size T. Yeah, so my template now only has one carrier in it. And each user I requests certain number of tokens in this template. So I know my Fi, I've computed it before. I only want to know how I spread out the tokens so it can be spread out evenly. So naturally, one would ask a question, is it possible that I spread out my tokens so my tokens are exactly T over Fi apart? So the answer is no. Suppose we have a template of 6 slots and I have 3 users. One asks for 1 slot, 2 asks for 2 slots, and third one asks for 3 slots. Then there's no way I can spread out the tokens so that they are exactly this many apart. So here's why. If I want to satisfy user 3, which asks for 3 slots, I would have to put them out like that. So once I've placed these 3 tokens, there's no way I can put out these 2 tokens so they spread out exactly evenly. So we can't do it exactly. So in the following, I'll just show you 3 very simple algorithms that, although do not spread out the tokens exactly evenly, they do a pretty good job. The first algorithm is based on bipartite matching. So, well, naturally, I need to create a bipartite graph. So on the left-hand side of the bipartite graph, I give all the tokens for each user. So for example, the green user asks for 3 tokens, so I put down 3 tokens. The red user asks for 5 tokens, so I put down 5. So on the right-hand side is my template. So I restrict where this token can connect to just to make sure that it's sufficiently spread out. So because the green one asks for 3 tokens, I say the first one can only go to the first third of the template. The second one can only go to the second third of the template, and the third one can only go to the last third of the template. And the red one has 5 of them. Is it 5? Yes. So the first one can go to the first fifth, the second one get to the second fifth, etc. Okay, so I make these edges as my bipartite edges. So now what I'm trying to solve is a matching problem. So I want to make sure that for each of the token, I connect it to one of these slots on the template so that any 2 different tokens would land on 2 different slots. It just so happens that with such a construction of the graph, this matching indeed can be done using Hall's theorem. So now if you believe that we have found a matching between the tokens and the slots, we in fact know that the desired slots are in pretty good places. Because what can happen in the worst case is that, for example, this green token gets to be matched in the very first slot in its third. But this one gets to be matched at the bottom of its third. So therefore, instead of exactly T over Fi apart, I'm 2 times T over Fi apart. It cannot be any worse off than that. Okay, so if I use this bipartite matching type of algorithm, I essentially get 2 times with a bit of a constant. Now, there's another very simple algorithm. It's called the golden ratio algorithm. That's invented by people Hoffrey, Aitai, and Rosenberg. It works in the following way. So we have an interval, unit length interval. First, we're going to put things down in a continuous manner in the following way. So if I have F1 tokens for user I, what I'm going to put down is first I'm going to put down a token at phi. Phi is this golden ratio, which is square root of 5 minus 1 divided by 2. I put it here, it's 0.6. And the second token, I put in a place called 2 phi, except that the interval is only unit length long, so I wrap it around. So the mod 1 will land me to about 0.2. So now suppose I'm done with F1, so I continue with the second user, which asks for F2 tokens. So F2 tokens, I start off where the previous user is left off. So I move to 3 phi. 3 phi is about 1.8, so I'm here. And then I'll move to 4 phi, it's about 2.4, 2.5. So I'm here. So I just repeat this process until I'm done with all the users. Now this places all the tokens in a continuous interval. The key here is that it defines the ordering in which the tokens are placed. So if we map this ordering to the template, to the discrete template, so that the ordering is preserved, we actually get a template design. And these people have shown that using this golden ratio algorithm, you are not. So T over Fi is the absolute ideal. And what you get is 2 plus epsilon, a factor of 2 plus epsilon off.
I'm guessing with this sequence, you will never
No, you
land on
won't.
exactly the same
No, you
place.
won't
So-
because it's a irrational number, so you won't. And it's,
But in reality, you have to truncate it, right? You
yeah,
cannot-
yeah. No, well, yeah, I suppose you need good precision, so.
Well, I guess the chance is very.
Yeah,
very
you just, you see, the thing is, this is not how you place the template. All you need to know is the order in which things happen. So you can always do that. Now, the third algorithm is even simpler. It's a randomized algorithm. Again, you have a unit length interval. And what you're going to do is, for user I, for say user 1, you have F1 tokens, right? You just randomly throw F1 tokens on this interval in a sort of uniform at random, and do the same thing for the second user, etc. And then you are done. So with some probabilistic analysis, one can show that the delay, this leading term is in fact the idealized T over Fi, except that there's an additive term which depends on the square root of n, which is the number of users, and the log of 2t, t is the template. Okay, so these are 3 very simple algorithms that work well for.
So this is the worst case.
Yeah, it's the.
This is the worst case.
No. Well, because it's expected, because, or maybe with high probability, because this is
So
assuming
this is with high probability, the what delay?
the delay defined with this formula.
I see.
So what you are trying to bound is how close together.
So then, I guess my question is, in the first 2 algorithms.
So this one is, this one, the first 2 algorithms are deterministic.
Right.
The third
I
one.
would expect the delay to reduce as the number of users increases. Right? I guess. No.
No.
No, that doesn't.
Yeah, so.
Never mind.
So the 3 algorithms are described in terms of single carrier. But because we have a relationship between a single carrier delay band and a multi-carrier delay band, so essentially the multi-carrier delay band is the worst case single carrier delay band over all carriers. So we can write these 3 bands from single carrier to multi-carrier. It's like that. So, but this is entirely solving a multi-carrier problem using a single carrier solution. So one would wonder if there's any way to improve the situation because you have multi-carriers. So there are 2 things one can do. Remember, this golden ratio algorithm, matching algorithm, in fact, is a deterministic algorithm, right? So one thing we noticed that if we introduce some randomization, so once you have a matching algorithm, for each carrier, if you introduce a random cyclic shift, you just kind of turn it for each carrier independently, and you can reduce the delay. it reduces delay in the sense that the term that maximize the max over all carrier T divided by FIC becomes this term, is T divided by the sum of the rate slot.
Can you elaborate on exactly what you mean by random cyclic shift?
Okay, so
the original algorithm is you do this independently.
So for each carrier, so suppose instead of saying now let me give you an extreme case. Suppose if it's the situation that the first carrier, second carrier, third carrier compute the exact same slot arrangement.
Okay.
So it's light green, dark green, light green, dark green, light green, dark green, light green, dark green. So what I do is I put a random number. Say instead of starting with at slot 1, I start at a slot that I choose at random. So this would spread things out even more. And the other thing is, so I guess I should have said that before. So T divided by FIC is kind of the ideal situation for each carrier. So what happens in the matching has a factor 2 on the delay, and golden ratio has 2 plus epsilon. Now random has the smallest 1 leading term, except that you do have an additive term. So the additive term is kind of, it can be big, it depends on the square root of the users. So one thing is, I mean, effectively you may want to reduce the number of users. So one thing is, if you have low rate users, many low rate users, you may be able to group them into fewer number of users called super users with larger rate. So this would be able to alleviate a little bit the square root term. Okay. So to finish off, I just want to show you 2 sets of plots. The first set is to illustrate, in fact, the usefulness of randomization. So I said we can add a random cyclic shifts to 2 deterministic algorithm. One is golden ratio and bipartite matching. So the top curve is the delay when we don't have the randomized shift. The bottom is the same experiment, except that we add some random shift to it. You can see a shift reduced delay in both algorithms. And the second set of plots, in fact, is try to validate what we observed in the bounds of the 3 algorithms. The leading terms, in fact, seem to be consistent with what we observe in the experiments. So golden ratio has a leading term of 2 plus epsilon. Bipartite matching is about 2, and randomized is 1 with a relatively large additive term. So these 2 experiments, one is for when the carrier numbers are relatively small and is with larger number of carriers. So we can see fairly consistent performance in practice with the bands that we...
Suppose instead of random shift,
Yeah.
you just continue the same golden ratio. So you finish your first carrier, you have an ending position.
Right.
What if you just use that ending position
As the starting position?
of the second carrier?
Yeah, I don't know. Wait. You're saying, I see.
That's sort of the logic that was used in a single carrier, right? You finish one user, then you just continue from that point on.
Yeah. But then what's the relative position of the...
Also, you just use that, I guess you just use that as a starting position.
I see.
So it's not a random shift, you just carry that over to the second channel. You do exactly the same thing you would have done, and then...
But I would imagine this would come out to be the same.
Any reason why
I would imagine it comes out the same as the non-randomized. Yeah. Yeah, I would.
Cyclic shift.
Yeah. Well, so I don't know, but I don't think it gives you the benefit. Probably it's fairly similar to the original one.
What you want to do is across different channels, you want to shake loose sort of this cluster of...
Yes, you want it to be independent. So you want it to be spread out. Yeah, interesting. Thought I could try to pursue a bit more.
In that case then, then maybe what you should do, well, not you should do, maybe one thing to do is you remember when was the last position when you finished user 1 in the first chapter. And then you use that as the starting position
for the second.
The first user in the second chapter. I don't know.
Yeah,
These
yeah,
are
it could be.
all very.
Yeah, it could be. I didn't think that way. Yes, yes, I could think. Maybe something interesting would happen. Yeah, I guess that would
because
involve.
that's sort of spatially, I think, spreads out among user 1's tokens.
But still, I mean, why would the leading term be any smaller than 2 plus epsilon? So that's
no quantitative
yeah.
insight here. Just
yeah, we could think about it. So I guess to finish off, I just want to just recap what happened in this talk. So essentially, we want to see how we can reuse the research results people have obtained over the years for single carrier into multi-carrier. For this slot-by-slot scheduling, we essentially have a very simple generalization of the max weight algorithm with a simple twist to make sure the resource is not wasted. So we get a half approximation. So in effect, one can do better than a half. It will be 1 minus 1 over e. It's better than a half. But nevertheless, it's a more involved algorithm. Unlike this as a simple gradient, it's just you can't implement it. So the open question is there any way you can use a simple algorithm to accomplish a ratio better than 1/2? And then there are also other issues. So in reality, there are always constraints that are not so easy to model. For example, if, say, there are constraints like if you have multiple carriers serving the same user, it's desirable that these carriers, consecutive carriers. So then how do you worry about that in your algorithm, etc.? So there's still work to be done on the topic. Okay, so that concludes.